Hello, everyone. Let's start today's training. The topic today is tunnel lining design. Let me go a little bit detail. We'll first review tunnel lining design methodologies, then how to model tunnel lining with visual slope. After that, we will discuss load and load combinations. Uh, Finish up with analysis, and we will use an example for that. First, let's review the methodologies. In tunnel lining design, there are two most common methods. The first one is called ground structure model, which considers the tunnel lining as a structure and the surrounding ground as a ground. Two of them interact with each other. This method, you can calculate the internal force of tunnel lining as well as ground deformation. So that's the advantage of this method. However, the shortcomings of this method are this method cannot consider load combination. And also, in most cases, the result from this method are not actually used for structure design, but just for variation and checking. So this is the ground and the structure model. The second model we commonly call load structure model, in which the tunnel lining is considered as a structure, and the interaction between the lining and the surrounding ground are simulated with springs in radius direction and tangential directions. And in this method, load combination can be considered, and the result of this analysis are commonly used for actual lining design. However, the disadvantage of this method is you cannot see the ground deformation or the stress in the ground. So these are two common methods, but each has their advantages and disadvantages. Then people will ask why there are so many software that you can be used for tunnel lining design, why you design a software in Visual Slope to perform a tunnel lining design. Visual Slope method is it's a combination of these two methods. First, Visual Slope uses the load structure method to calculate the internal force and the deformation of the tunnel lining. The result can be used for actual design. Then use this result embedded into the ground structure method, so you can also see the ground deformation and the stress in the ground. So it's a combination of both to overcome their shortcomings. So I just have a quick review of the visual slope method. Then how we calculate the springs in tangential and the radius, you can find a reference from Army Corps Engineers recommendation. These are the formula I just reference for that. And using visual slope, you can model circular shape tunnel section or TBM segments for tunnel design. And you can also simulate horseshoe shape tunnel sections. Let me just go a little bit, turn off. The more complicated you can use any shape. Say if you have very complicated sections, you can always use any shape to simulate that. Then once you establish the model, then you can set up the loads like grounding pressure, vertical and horizontal pressures, as well as hydraulic static pressure like water pressure. Once you finish all the settings for the load, then you can do a load combinations, and you can go up to 4 different load combinations. So we will go over those with the example. After that, you can make analysis, and you can have the bending moment, deformation, something like that. Once you finish, you can run a 2D FEM. It will automatically give you the ground deformation and ground stress, so you can have a both. That's the way visual slope does. Now, after finish reviewing those, I will give you an example. It's a real example. There are 2 options for this one. It's a water tunnel, and there are 2 options. The first option is use TBM. We need to design a segmental for the TBM lining. That's one option. And the second option is use drill and the blasting method. In that case, we need to set up an initial support using steel sets to support the excavation. After finish, we will set up forms, then cast concrete to make a tunnel. So there are 2 different methods for this tunnel, and we will design those with visual slope. And the ground condition, we have rocks that was classified as classes 3 and classes 4. So we just use one of them for this example. So now let's go over for the modeling part first. I will open visual slope. I'm browsing to example. In this example, the section is a horseshoe-shaped tunnel. We just want to review how this shape can be made with visual slope. So first, I just delete these so you don't need it. Finish that, I will use generator. Go to the tunnel generators. And this is the tunnel generator. For this section, we need go just a few parameters. So I just go a little bit in each case. Let's see from the top. We can have a circular shape. If we click circular shape, and what you need are 3 parameters. The first one is the x coordinate of the center, and then y coordinate, then the radius. Once you have those, and you can check for what type of material you want to use. So I just say we want to use W8 by 40. And for tangential spring, if you check, then it will generate tangential spring as well as radius spring. But for circular shape tunnel, the tangential shape is strongly recommended. Sorry, somehow the this is turned on. I would just turn it off. Dennis, your camera is on. Could you turn it off so no one would see you? But if it's not, that's fine. Okay, it's gone. All right. So we have three parameters, and after that, you can click View Diagram. So this is a circular shape it will generate. And if we zoom in, you will see the tangential spring as well as the radius springs. It takes a little bit. Okay, you can see that. This is the radius spring, and this is a tangential spring. For the circular one, I strongly recommend you use tangential spring. Otherwise, it's not a stable structure. It can rotate. So when you calculate, you will find some unusual result. So you have to use tangential spring along with radius spring. So it will take a while and go back. This is the circular one, and you can also do the horseshoe. It's a straight wall and have a arch on the top. So besides three parameters, we need another one, which is the height of the wall. For this case, h is this. If we put this in, once we view this, then you will have a different type of tunnel section by 4 parameters. Then you can go on to the next one. If you have 5, 6 parameters, you have the bottom width, which is from here to here, and top width is from here to here. If you put these in, and you do again, then it will give you a different shape. And we can go on to furthermore, say this is something like that. And you also add a curve under and give the radius of that. And I will also give the radius for the corner, say, and you can go. You can find a different one, something like this. So you can do any type of shape you want to. Next example, I just give you any shape if it's more complicated. So to save time, I open this one, which does not have anything yet. And we go in there, and we go tunnel generator. And it is any shape. If we click any shape is you can use a combination of curves and straight line. You can create any shape for the tunnel sections. Sorry about that. It starts from the top of the curve, that's point 1. And we need to give the top, say for this one, we say it's arch only, so it's curve only. And the first point coordinate is this point. We say x equals 15, y equals 15.4. So once we finish that, then we need to give the center of this curve, which is x equal to 15, y equal to 8.5. So we have a first curve. And finish that, you give the center of second curve. And the third curve, the fixed curve, and you can go on as many as you want to, but those centers should make sense. Uh, so the curves can be tangentially connect to each other. If they cannot be, then when to calculate, it does not make a section. So it has to be uh, tangentially can be connected. So you do not need to have like a radius, because once you give the centers, and it will automatically connect tangentially. So it will figure out what's the radius is supposed to be. So once we have those in, you click views, so it will give you a shape you want to, and you can modify those to modify the sections. So this is how visual slope does uh, does it to make a cross section of a tunnel. You can change those very easily to uh, make the bigger, small, very easily, because I had a project just like that, and we use a different program. And since in the initial stage of the design, the shape can be changed, the size can be changed, so it's going to be so difficult to use other programs to redo a cross section. But with visual slope, you can just change a few numbers. It will make a, a section very easily. So now let's go over the example. Then we will just go through these, and then we will know how actual visual slope works. So this is the example I mentioned before, and we have a water supply tunnel, and we need design two different support. One is for drill and blasting method. We need to design a steel set to support the tunnel initially. After that, we will use the form to create the circular tunnel by casting concrete. So let's review the material we have. We have two types of material. Soil material we call class 3 and class 4. And then we just say class 4. We have the density for that. We also have the modulus, elastic modulus, and the Poisson's ratio. These two numbers will be used for the spring constant generally. So we need these numbers. In this case, we just have like a tunnel in one uniform material, but it can be in different type of material, and you can have it on the sections here, and it will generate the constant directly from the surrounding material. Okay, so this is the rock material. We also have for the structure itself, we have three different types of material. The first one is W8 by 40. We'll just open that, and this is W8 by 40, and you have EI, EA, and the Poisson's ratio, the self, the weight, and the longitudinal spacing. It should be 3 feet, and the self it should be 4 to 5. So we have these, and also we look at W8 by 48, which is for the bottom portion of the steel set. We still have the 3 feet, and we still have 4.5. All right, and we have segment. Segment is, this is a 5 feet, and we say that's a 3 times So we have those. So we have all the material ready for this. And we can go into the generator. The generator, we just need the center of the curve here and also the radius, as well as R1, which is the radius of the bottom curve. R2 is the corner. We have 0, just say 0, we stay 0. And the height, which is 10.6. The bottom width is 16. So we have this is 16. And the tangential, the top width is this point. We have 21.2. So after that, we create the model. This is the model we can create, and we enlarge, zoom into it. So this is the model itself. However, the bottom should be a different material. So we just add the material to it. This is here. I need to go one by one. Yeah, it takes a little bit long, but just to be with me. Okay, we change the material to it's supposed to be. We can also add hinges if needed. Say we need hinges here, you can add hinges here. So at that point, there's no bending moment at that point. So we have 2 hinges right there. Now we finished the modeling. After that, we need to consider the load. The load including water pressure. If it's negative, which means it's towards to the tunnel. But for this case, we do not have water pressure, so it's still there as 0. And there's also grouting pressure. If it's a TBM tunnel, we needed that. But for this one, we just have vertical and horizontal pressure for these. So you click vertical load setup, and we have the one we give a name and give the pressure we calculated. And once it's negative, it's towards the tunnel. So at that point, it's 1800,444 as the pressure. At this point is the same, but it does not need to go all the way to the edge. But for this case, it is. So we have A and B are 0. So this is the one. You can continue to add another vertical force. For this case, you can add up to 4 vertical pressures for each project. Once you close, you can also do the same way for the horizontal, and we have a horizontal pressure similar to what we have before. Okay, so once you finish those, you close it. Now we can do a load combination. Here is the load combination. The first one, we consider the self-weight. We do not have a hydraulic pressure. We do not have grouting pressure, so it should be 0. And for the first one, the vertical equals 1, and horizontal equals 0. We have a first combination. And the second combination, we also do not have grounding force. And for the vertical, we have 1. For the horizontal, we have 0.5. So this is the second one. And the third one, we have self, but we do not have a grounding force, and have a vertical 1 and horizontal 1. So we have 3 different combinations. So that's the load and the load combination. Once we finish, we can close that. So use this page to set up the model and also set up the load and the load combination. So once we finish, we close out that, and we go back to the normal size. So this is the tunnel section. Now we need to do analysis. We're going to the analysis panel, click on tunnel, and we can consider the ground condition. So once we finish ground condition, it will run initial calculation to remove the movement caused by the ground weight itself. So this is the initial. After we finish, we run an FEM analysis just for the tunnel itself. So this is under load combination 1. This is the bending. You can see the bottom is quite a bit bending. So we need a heavier section for the bottom. This is for section 1, section 2, combination 2, and combination 3. So there's a different type of bending moment. We can also see the structure deformation. You will see it's heaved and maybe a little bit here, but out of there it's almost it's going inside because we have a pretty heavy horizontal force. This is for load combination 3. And if we want to see the ground movement for load combination 3, we can just exit this. And then it will use the load combination 3 to calculate the ground movement. Let's just see how you can see this is heaved and there's something is pushed in. It should match exactly as the tunnel lining deformation. And you can see the vertical movement. So you can see that at the bottom there's a heave up, but on the top there's some movement. Actually, it's moved up because this under the lateral pressure, this structure actually was squeezed horizontally, and the top actually moves up a little bit. So that's give you the deformation of the ground on the load combination 3. But you can do the same way for load combination 1 and 2. So this is the way you can design the tunnel as well as you can see the movement of the ground. If you are interested, you can also see the stress. Let's just say the vertical stress. So this is the total vertical stress in the ground. So this is for the steel set design. Use similar way we can design with TBM tunnels. So let's look at how do we do TBM tunnels. We're going to the generator. Instead of use the horseshoe shape, we use circle. Of course, you can just say circular. It will be something like that result. However, TBM segment, between the segment, there are hinges, elastic hinges. Uh, some design you can consider some design. If you make it simple, you can just reduce the overall bending modulus, or you can do each individual considering the hinge elasticity. So what you can do is you choose TBM lining, and once you choose, there's a table shows it starts from uh, each uh, joints, and you need to give the angle of each joint. So let's just do that. The top one is 11.5 degree, and the rest are 67.5 degrees. So we need to give the angle from the top for each joint. So let's go for that. Fine. Okay. The first joint is at 11.25 degree from the top, and we have hinges, and the stiffness of the hinges from 0 to 1 of the original stiffness of the segment. So if it's a 0, which is a perfect hinge, and at which the bending moment should be 0. If you choose 1, then it will equal to the segment, and which also means there's no hinges. But I just choose 0.5 for this case. And the next one would be 78.75, and we have a hinge and 0.5. And the next one will be 146.25, and I have a hinges with also 0.5, and go on further. 13.75, and this is 0.5. The next one is 281.5, and I have hinges, which is also 0.5. And the final one is 348.75, and I have hinges, also 0.5. So once you finish that, I need to make sure they are right. 11.25, 78.75, 146, 25, 213, 75, 281.5, and 348.75. So they are all correct. And once I finish that, I also need to make this is 5 feet because it's a 5 feet spacing, and I need to choose segments. So you have those, and I just assume the load condition is the same as the previous one. Actually, it's not, but to just save time, we assume it's fine. And then you can view the diagram, and you will see this is the structure with elastic hinges here. So once you finish, you close, and you can run analysis again. And the similar things you can do is, oh, I'm sorry, I forgot something. Let's go back to the generator. In this case, say if we have a grounding pressure, say we have a grounding at the top and also two sides at the spring line. So what we do is we have a starting angle uh, from also from the top here. We say it's from 0 degree to 5 degree to 5 degree. We have a pressure. Just to say it is 1,000. We need to use negative because it's towards the excuse me. It's towards the tunnel. And the next one is 85 degree to 95 degree. It is also 1,000. And the next one is 265 to 275, which is also 1,000. After that, the top, we have another one, which is 355 to 360. So we have these. All right. So we have a grounding force. Now this time we need to change the load combination. The first one, we just have a self-weight and grounding force without vertical pressure. The next one, we have this equal to 0, the horizontal equal to 0. And the next one, this should be 0.5. And the next one, before we did not have this combination, we add one in. This will be 1, 1. So in this time we have 4 different load combination. So we finish that, we close it, and we close everything. Of course, you want to save that if you want to. Let me just save it as a different one. Okay, we save that, and now we run analysis. Include ground condition. It will calculate the initial movement caused by the weight of the soil itself. Once you've done that, we do analysis for okay. This is the first under the first load combination, which is the you have a vertical pressure and also 2 horizontal pressure makes something like this. Also, the weight of the structure itself. You can do the second. See if this is the bending moment, and this is the structure deformation. You can see it's pushed down and pushed out, something like that. But if you have a very weak material around here, then this will be even more for the horizontal movement at this location. So once we say, I want to see what kind of a ground deformation would be under the load combination 2. So we turn off that, and it will make a calculation for you. Okay, you will see this, the tunnel lining, the top move down and the bottom move up, 2 sides move away, and you have some settlement on the top of the ground. Let's see what we have for the vertical deformation in this case. You can see this is the settlement due to the tunneling of this. If you want to see the details, you can always use this line to make the number out. So this is the settlement around this line. You can copy it to like a spreadsheet, copy and paste to a spreadsheet. So this is the ground movement. And you can also see a shear stress for the ground due to the movement. Okay, you can have this. So these are the stress field and the deformation field for the ground. Okay, so these are the way you can use a visual slope to do tunnel lining design. I finished today's old content. If you have any questions, you can ask. If not, we just end here. Have a good holiday and a good weekend.